Now we want to calculate the potential energy at various positions and kinetic energy for an oscillator. And you can think in terms of what we got for this oscillator, total energy of 0.625 joules, and total energy at any point being the sum of potential and kinetic energies. Well, potential energy of any oscillator at position x relative to equilibrium is 1/2 kx squared. So, in particular, at position A, which is A standing for the amplitude, which is the greatest potential energy can have because the amplitude occurs when the position is at its maximum distance, when the position from equilibrium is at its maximum, is 1/2 Ka squared. So, this is all the energy the pendulum has, because when it's out here, it stops before it comes back. This is as far as it goes. It has to turn around. It's stationary for an instant at that position. So that the total energy is just this. We're not adding or taking away any energy. This is a conservative system. Now, this is an ideal system. Actual systems are generally not conservative except at the subatomic level and in, again, ideal conditions. So there's no energy being added, so any kinetic energy that we get has to come at the expense of potential energy. There are no non-conservative forces acting, so the sum of kinetic and potential energies is 0. Well, then, what is the potential energy at position x? Well, potential plus kinetic energy is equal to the total energy. At position x, the potential energy is 1/2 kx squared. So our potential plus our kinetic is just kinetic plus 1/2 kx squared. But our potential plus kinetic is the total energy, 1/2 Ka squared. So kinetic plus 1/2 kx squared is 1/2 Ka squared. Follows that our kinetic energy is 1/2 Ka squared minus 1/2 Kx squared. Now that's not a formula to be memorized. You simply understand that at the extreme position we have energy 1/2 Ka squared. At position x, it's 1/2 Kx squared. The difference has to be our kinetic energy. So there we have it. The potential energy at maximum position minus the potential energy at this position is our kinetic energy at this position. So the kinetic energy is this. Now, we can factor it out and get this strange looking formula, 1/2 K times A squared minus X squared, that completely loses the connection with the fact that this is the potential energy, maximum potential energy, total energy of the system. This is our potential energy at the point. Difference in the potential energies is the kinetic energy. That is our physics principle. Our physics principle is not an equation to be memorized. It's a principle to be used and thought through every time we apply this. Okay, so there's our equation. Now, you can memorize equations and use them, or you can learn the physics and reason from the physics. And I understand, as I say often, that you're between the rock and the hard place. You have more to do than can be done. Well, almost everybody is in that position. If your IQ is less than about 160, and you got to make trade-offs, and sometimes you got to memorize a formula. Just realize when you're doing it that you are substituting a formula for understanding. Now, formulas are great; they're handy. You want to check and make sure that your understanding agrees with the formulas that you know have to be. But the way we teach this course, the way I teach this course, we proceed from principles. And if you do otherwise, you're doing it against my advice, but I don't hold that against you. If you can get the right solution, it's okay, as long as you solve it in the way I say. Okay, well, anyhow, here it is. There's your potential and kinetic energy relationship for any harmonic oscillator, any simple harmonic oscillator.